We saw in the previous video that a wave is a disturbance that propagates with some velocity through a medium. We also saw that depending on the direction of the vibration with respect to the direction of the wave propagation, waves can be classified as either transverse or longitudinal. For transverse waves, the displacement of the medium is perpendicular to the direction of propagation of the wave. In longitudinal waves, the displacement of the medium is parallel to the propagation of the wave. Irrespective of the type, the wave velocity is given by the relationship v is equal to f lambda or v is equal to lambda on t, where f is the frequency of the oscillation, t is a period of oscillation, and lambda is the wavelength of the wave. So does this mean that a faster oscillating disturbance will propagate at a higher speed? Well, it can be shown that the velocity of a wave depends on the properties of the medium in which it travels and not on its frequency or wavelength. The speed of sound in air, for example, is about 331 meters per second at standard temperature and pressure, irrespective of the frequency or the pitch of the sound wave. Electromagnetic waves, such as light, are moving with a speed of 300 million meters per second in space. But let's consider a case of a one-dimensional traveling wave that propagates on a stretched string. It can be shown that the velocity of a wave on a stretched string or cord depends on the pulling force or tension in the cord and on the linear mass density or the mass per unit length of the cord. This relationship is given by the formula V being equal to the square root of the force divided by the linear mass density. The latter is represented by the Greek letter mu and is given as the ratio of the cord's mass to its length. In the case of a stringed instrument, for example, mu indicates what material is used to make the string or how thick the string is. Each string in a guitar, for example, has a different mass per unit length value, and as a result, a wave would travel at a different velocity along each different string. For a given string, however, the wave velocity can be varied by simply turning the tuning key. Doing so changes the tension on the string so that an increase in the tension will increase the wave velocity, while loosening the tension will result in a reduction in the wave velocity. As we will investigate in a later video on the phenomena of standing waves in resonance, an increase in the tension not only results in a higher wave speed, but also a higher frequency or a higher pitched sound, since it can be shown that by rearranging the equation V being equal to f lambda and solving for f, then the frequency can be seen as being proportional to the speed of the wave. Now let's have a look at an example. Consider a uniform cord of mass 0.3 kilograms and of length 6 meters that is stretched by attaching a block of mass 2 kilograms via a frictionless pulley. Assuming that the cord is disturbed by generating a pulse at the wall's end, calculate the speed by which the wave pulse will travel along the cord. We can solve for the wave speed using the velocity equation if we know the tension in the cord and its mass per unit length. The block that is hanging off the cord hangs with the force of gravity being equal to its weight pulling it down, while the tension in the cord is holding it up. Provided the block is not moving, then the two forces must be in equilibrium. Or in other words, the tension in the string has to equal the weight of the block. As for the cord's linear mass density, it's defined as the cord's mass divided by the length. Putting these two equations into the velocity formula gives us the velocity being equal to the square root of the weight of the hanging block divided by the mass per unit length of the cord. Substituting the known values into the formula gives us a speed of 19.8 meters per second. When rounded to two significant figures, this comes to 20 meters per second. If the pulse moves with a speed of 20 meters per second, how long will it take this pulse to travel the length of the string from the wall to the pulley, which is 5 meters long? In general, the velocity of a wave traveling through some medium is dependent on the elasticity of that medium and its inertia, and is given by the velocity being equal to the square root of the elastic force factor divided by the inertial factor. In the case of a wave in a string, the elastic force is the tension in the string, and the inertia is its linear mass density. In the case of a wave traveling through solids, that equation takes the form of the velocity being equal to the square root of the elastic or Young's modulus of the material, y, divided by its volumetric density, rho. For a wave traveling through a liquid or gas, that expression takes the form of the velocity being equal to the square root of the bulk modulus of the material, b, divided by its volumetric density.